Okay, I'm calling this lecture Mom, Where Do X-Rays Come From? Because I want us to get an idea of how the discovery of X-rays came about, as well as the discovery of other types of radiation, and what those implications were for people's safety, right? So here are my learning objectives. We're going to talk about some pioneering scientists who are responsible for the discovery and development of X-rays. So no one made X-rays. X-rays can't be patented, right? They're natural phenomena that occur in certain artificial situations, right? But it's a physical property of the universe. So people discovered them and then developed them. And then we're going to talk about the safety concerns related to X-rays, which we've alluded to a little bit already in the first class. We're going to talk about measures needed for radiation safety, talk about the units of measure that we'll use for radiation, and then there's an opportunity to get some free stuff. I'll show you where there's some free stuff, like an ebook. It's actually a pretty good ebook. I liked it, you know. I feel like I'm that internet blog marketer at this point. Sorry. I was excited about it. I would say the pioneers. So Newton famously said that he got where he got, Sir Isaac Newton, by standing on the shoulders of giants. So these are the people who who did the science that would lead up to the use of X-rays, right? So Michael Faraday, right? You may have read about him in your textbook. Does anyone recall what he did? What did Faraday do? He came up with a number of laws related to electromagnetism. So we will look at Faraday's law when it comes time to understand how the stators work on the X-ray tube, as well as other magnetic phenomena. William Crookes, we've alluded to as well. He is the British scientist who developed this tube that's illustrated here. And this is an actual photograph from the Oak Ridge University Museum. And this is a Crookes tube. So y'all may remember that tube that I showed you that glows in the dark with those creepy rays, and it made that cross of Malta in the back. This is exactly that tube. So if you hook this thing up to a car battery, that's exactly what it's going to do. It's going to produce X-rays, and as well as some cathode rays. So Crookes is the man who developed this weird, crazy light bulb tube thing, right? George Eastman, the name may be vaguely familiar. So Eastman Kodak, he was a chemist here in America that developed emulsions that we could use for photography, right? So he developed a lot of what became influential to X-ray film. Almost every X-ray film I ever produced was a Kodak film, right? And then Pierre and Marie Curie were a pair of they worked primarily in France. They were originally from she was from a different country. I believe she was from Romania. He was from France. They were married, and they worked early on in understanding all the different refinement processes that needed to occur to get usable radioactive materials. So they refined, and actually I misspoke. She was from Poland. Because they named polonium after her nation of birth, right? But the Curie is still the unit of measure that is frequently used, a traditional unit of measure for radioactivity, right? So their work in radioactivity went on to inform us with a lot of radiation protection measures. She was also an X-ray tech of sorts. Madame Curie, her and her daughters went out, I believe, during World War I, with an X-ray tube on a horse-drawn wagon, and we're taking X-rays of troops who were injured along the front. So really interesting woman, someone who was an amazing scientist, but who also didn't remove herself from her role as a civilian. And then Henri Becquerel, he is the man who is credited with the discovery of radioisotopes and radioactivity. So within a year of Roentgen's discovery, in 1895, we have Becquerel making his discovery that uranium is capable of very similar phenomena, right? And so he went on to pioneer a lot of work in that. And the becquerel, interestingly enough, is now the SI unit of measure for radioactivity. But there's a bunch of other scientists that we're also interested in, right? And these are pretty interesting folks. So we have Hittorf, who was a German physicist who co-invented the Crookes tube. We have Ivan Poye, who designed vacuum tubes. This is not a cleaning device, but he figured out how to do different vacuum discharge things. So these people were innovating with physics at their time to look at different ways that these wave phenomena could be created. Nikola Tesla, you've probably heard of him. Very strange man who invented a lot of things. And he also was possibly magic. And he is believed to have discovered X-rays prior to Roentgen, but it's disputed. He didn't write anything down about it. He just claimed it. The claims are very believable because he went on to discover a lot of things that other people went on to use and exploit. So he probably discovered long before anyone else how radio waves work, how to produce radio waves. Is possible that he is the one who identified the Bremsstrahlung process. Like, he mentions the stopping process that produces X-rays. So it's still is a point of historical controversy, but it's thought that Nikola Tesla created that term Bremsstrahlung. Have y'all heard about Brems yet? Has Tom talked about it? Okay, we'll talk about it soon enough. It's not the name of a German death metal band. Fernando Sanford also detected X-rays in vacuum tubes. Philip Lenard won the Nobel Prize for Physics for discovering a lot of properties of cathode rays, but he was also a Nazi, right? So already there's kind of ethical implications we can imagine for some of these discoveries, right? So Lenard would go on to work along with the Third Reich towards development of nuclear weapons, right, to be used by the Third Reich to take over the world. Wilhelm Roentgen was the first person who discovered and then systematically studied X-rays, and he won the first ever Nobel Prize, and he married a really smart girl, like we've already mentioned earlier. And then Edison, Thomas Edison in New Jersey, examined calcium tungstate and a lot of other chemicals, like hundreds of chemicals that could be used for different X-ray purposes, whether as emulsions, as fluorescent chemicals, as contrast. So he's the person who discovered that barium could be used for X-ray contrast, iodine could be used for X-ray contrast. And he also electrocuted to death a whole lot of elephants in order to prove Tesla wrong, right? So if you're curious about that process, you can check out the Drunken Histories on Tesla versus Edison, and it will fully explore all of that. There's also, I'm sure, a number of other documentaries about it, and it's where the band AC/DC gets their name from. Okay, so Roentgen is this werewolf here who developed the first X-ray. And he systematically studied them and won the Nobel Prize. And the way that I remember this date is important. It will probably be on the registry. November 8th, 1895, is by remembering Anna Bertha Ludwig, his wife, that on 11/8/1895, Miss Ludwig was glad to still be alive. Right? That's the way that I remember. Miss Roentgen was glad to still be alive. And she's not a vampire, even though she clearly looks like one in this photograph here. But you can't photograph vampires; they don't show up because of the mirrors used inside of cameras. That's science. Did you have questions about photographing vampires? Okay. All right. So this is a photograph of the first ever X-ray taken in the United States of America. And what's interesting about this picture is that thing that's glowing there right by that young man's eyes and thyroid is an X-ray tube, right? Trained on both on. I like that they were able to aim it both at his eyes as well as this man's gonads that's standing to the right of him. They did not understand anything about shielding at the time. But what they did understand is that this young man had hurt his arm while he was skating on a frozen lake near Dartmouth in New Hampshire. And they were able to create the first medical x-ray on a living subject. The exposure time, I believe, was 8 minutes, if I remember right. And the reason for that is because of the weakness of the x-rays that were being produced, as well as the lack of understanding about how the photographic process worked for x-rays. So they were actually using the x-rays to expose the film. We would later learn that you could use an intensifying screen to intensify the light in order to get a film much quicker. But this was within a year, actually a series of months. So Roentgen made his discovery in November. I believe this was in February or March of the very next year. So within a series of months, we already had medical application of x-rays, right? This guy was super smart. He was a dentist who was using x-rays in Boston. And he was the first to develop collimation and filtration. And he was also the first to start using some kind of shielding apparatus. So he recognized that radiation was causing burns to his hand in experiments as early as 1898. So again, within 3 years of the discovery of x-rays, we have the first people recognizing that not everything about this is good, right? I want to point that out because honestly, real protection measures don't begin for almost half a century. We're really slow on the take. It's like, they say, hindsight's 20/20, right? But we have to ask, why didn't people care that the stuff was burning their hands, right? And the reason for that is we kind of have to jump into our time machine, right, with Bill and Ted and go back in time a little bit and think about this day and this era, right? This is a time when Coca-Cola literally had cocaine in it, right? That would be an exciting time to be alive. Like, we have nothing on them. Like, they were so much smarter than us. But for real, they thought that science at that time, prior to World War I, World War II, that science was going to be the salvation of mankind, that through science we would liberate all peoples, that we would, raise the common standard of living, and all those types of things. And so when we discovered x-rays, when we discovered radioactivity, everyone was just like, this is amazing, what else can it do? Let's slather our bodies in it, let's drink this stuff. So that's exactly what all these products are designed for. We have x-ray headache tablets, which probably had radium in it. This is a uranium comforter here, that yellow thing there, where you could sleep with that, perhaps, I don't know, on your crotch. It's supposed to help warm up your body and improve vitality, which I think we've already talked about. And, you can sleep with it maybe under your pillow. It might give you interesting dreams, those types of things. It would definitely help with bone pain. But we had it in our shoe stores, so that's an x-ray fluoroscope there, where, if you're not sure if your shoes were fitting, like you had, I guess, no nerves in your feet and couldn't tell if your shoes were fitting or not, you could x-ray your feet wearing your shoes, along with your mom and the salesman, and they could convince you that these shoes are actually fitting, forget what your feet are saying, right? And notice that this cabinet's made out of wood, too, and that the x-ray tube would, again, be roughly at the level of your crotch. So... glad I got these shoes. I don't know why I hurt so bad. All of these things here, these marbles, these pieces of glass, they're all radioactive, right? So standing at this cabinet while I was taking these photographs at Oak Ridge, I had a Geiger counter with me, and it's ticking away, right? All of this stuff is radioactive. So your uranium glass, Fiesta ware, marbles, little tchotchkes, all sorts of stuff. Now, the stuff at the bottom is not radioactive. Simpson's coffee cups are not radioactive, right? But there was, in retrospect, kind of a revision of that, right? Where people started wondering, like, what on earth were these people thinking? So something changed between that photograph on the bottom left and the photograph on the bottom right. If you're curious about ways to kind of learn a little bit more about this, what I'd like you to do is use your textbook and a sheet of paper to kind of come up with a timeline for this so that we can understand what happened, right? And what order these things happen, because I can lecture about it all day long, but I do think it's going to be more helpful to us if we kind of invest a little time in our textbook. The textbook does do a good job of laying this stuff out. Okay, hopefully it's helpful to get a little bit of context around here. Now you may be wondering in the back of your mind, like, what is he going to ask questions on about all of that discussion, right? What is this? Like, is this a history class all of a sudden? No, all I care about is that you know that X-rays were discovered when? Yes, and then we're good. The rest of it's just context, right? Why did I tell you all that other stuff? Because my goal for you is not just that you're going to graduate this program and go on and become an X-ray tech and land a job. It's that within the next, 5 to 10 years, you'll be a millionaire, right? And be giving generously to the Baptist Alumni Fund, right? And that there'll be a scholarship named after you here at the school. Those are my goals for you, right? That you'll all be millionaires. And in order to be a millionaire in this world, you need to kind of think about context quite a bit and use some critical thinking skills. That's why I gave you all that information. Well, let's talk a little bit more about this radiation stuff. We've talked about how we made it inside of the X-ray tube, and I'm sure that Tom is going to give you some really helpful stuff about it in the physics class. But for the purposes of our class, we do need to talk about it some. The video showed us a little bit about it, but basically radiation is an energy form. And what is an energy? Energy is something that does work. Oh my Lord, there's a really bad joke on here. It likes to move it. I should be fired for making that. What is it moving? It's moving stuff that don't like to move, right? That's what radiation is, okay? So we can apply that term to a lot of stuff, right? One of my favorite things to harp on is when the ultrasound techs say, and we don't use radiation. It's like, oh, really, you don't? Then how did you get that freaking picture, right? You used radiation, you used mechanical radiation to take that picture, right? So it is different from electromagnetic radiation, granted, but you did use radiation. So radiation is kinetic energy, it's work-doing energy that moves through space, and there's a crap ton of different types of it, right? So it's important to think about those different types. The type that we're going to use the most is electromagnetic waves. That's what X-rays are. They're electromagnetic waves. We call them electromagnetic waves because electric and magnetic fields fluctuate as they travel through space. So they're going to oscillate in space, and those oscillations cause changes in electrical fields as well as magnetic fields. So, I don't know. Have you ever been listening to the radio when there's a lot of solar flare activity, right? There will be more static in the radio. Why? Because the radiation from the sun is literally causing changes to the electromagnetic fields that are producing the radio waves. So we characterize these by their frequency and wavelength. So you'll get to do all sorts of formulas where you calculate frequency and wavelength, right? But the reality is they also behave like particles. They have the ability to ionize things. With sufficient energy, they can ionize stuff. So what we're saying is that this is a radiation that can travel through space in the form of a wave, but it can interact with matter as though it were a particle. So one of the terms that we use, like one of the AKA terms that I might use for X-rays, is that they are photons. The term photon refers to something that's capable of behaving like a wave and behaving like a particle. And I may have mentioned it in the past, but if you ever want to really freak yourself out about the stuff that we're doing, you can look up what's called the double slit experiment, where, and it's on YouTube, it's very interesting. It's looking at trying to define what this X-ray is. Is it a wave? Is it a particle? If you do an experiment to determine if it's a wave, it will behave like a particle. If you do an experiment to determine if it's a particle, it will behave like a wave. It's actually kind of watching you, and it knows that it's being observed. That is really strange. Did you? Great. Interesting stuff. So we rely quite a bit on the theory of relativity to understand what's happening, right? Now, I'm not expecting you to know all the crazy parts of the theory of general relativity, but you do need to know that it means E equals mc squared. In this case, E equals energy, right? And mc equals the mass or the matter and the speed of light, right? So what this equation allows us to do is that if we destroy matter, we can produce energy, right? If we do other things with matter, we can actually absorb energy and things like that. So this equation was what led to the development of things like the atomic bomb. But it is helpful for us to know that these X-rays exist on this spectrum, right? And I like this illustration of it because it's showing the length of the wavelengths in relation to everyday objects, right? So at the radio wave wavelength, you've got things measured in basically kilometers, right? So the best everyday object you could think of would be like downtown New York City would be like a wavelength of a radio wave, right? Versus something like a microwave, it'd be like the wavelength would be like the width of a butterfly, basically, right? Once you get into the range of visible light, the wavelength would be microscopic organisms like protozoans, right? Once we get past visible light, so on the visible light spectrum on one side has infrared, that means less than red, then you have the whole visible light spectrum, and then you have ultraviolet, that means more than violet, right? At the UV range, the wavelength is roughly it could be measured in molecules, right? So that wavelength is compressed a lot, right? And it is now capable of ionization. The thing about this, and something I'll point out about this, is which one of these wavelengths is traveling faster, the X-ray or the radio wave?
The X-ray.
The answer is they're all traveling the same speed. They're all traveling the speed of light. So that's that E equals mc squared tells us the speed of light is a constant. That's what's important about the theory of relativity. That we understand that the speed of light is a constant, all of this electromagnetic spectrum stuff is traveling at a constant, roughly 3 meters per second, right? Which is really, really freaking fast. Okay. So we can use this little equation to help us understand this better, right? But I find that most students don't like this equation for whatever reason, right? So the way that I generally think about it has to do with this guy, this character here from National Lampoon's Christmas Vacation, who, I don't remember what happens, but he says to Clark, "That's pretty low, mister. If I had a rubber hose, I would beat you with it," right? And well, imagine that I had a rubber hose in this classroom. I'm not going to beat anyone with this rubber hose, though. It's a really long one, and it's going out the door, right? And I am making waveforms in the rubber hose. I'm running the rubber hose up and down, right? You know what I'm talking about? And it's making little waves down the length of the room, right? If I need to go get an extension cord, I can, I guess. But I'm going up and down, right? So for the waves, in terms of their energy, they're all traveling the same speed. But if I want to change the amount of energy that they have, I can go up and down quicker, right? If I go up and down quicker, now I've got a waveform that's got a lot more energy, right? How are the waves going to look? Are they going to look bigger or smaller? They will look smaller. That's the whole point of this equation. So forget about the math, just think about it in your mind. I've got the rubber hose, I'm running it up and down. If I'm going up and down nice and slow, the waveform is going to look long, right? It is low energy, right? If I'm going up and down really fast, that's a high frequency, right? That's what high frequency means. If I'm going up and down really fast, the waveform is going to look really small because it has more energy. That's what we're talking about here. If it has sufficient frequency, if it has a small enough wavelength, if it's something at ultraviolet light or smaller, we have the ability to do ionization. Ionization is a magical event, right? More powerful than love, probably. I don't know. Love might be more powerful than ionization, but it does produce something very, very interesting, right? When we have a photon that have sufficient energy and interacts with an atom, it can knock an electron out of the electron cloud. Now that may not seem like that big of a deal, but trust me, it's a big deal to that atom, right? It will never be the same again. It will always remember that electron. So, sorry. What results from that is what we call an ion pair. You can think about, like, have you ever seen one of those lockets where it's like half of a heart, you know, and someone out there is like palmed the other half of the heart? That's what's going on here. The ion pair means that there is now what used to be a couple, right? This one atom with its electron that it loved. Now are two different people that hate each other, right? There is now a positively charged atom because it lost an electron and it will never be the same. It's scarred for life. And there's a negatively charged electron that hates everyone, right? That's why it's called an ion pair. And that process that I just reviewed is called ionization because it produced an ion.
And when did you say ionization can happen? You said just when there's sufficient energy in the photon?
Yeah, we've got a high enough frequency. Anything from ultraviolet light and higher frequency can produce ionization in the electromagnetic spectrum. Now, I wish it was as simple as that, but it's not, right? Because of that guy Henri Becquerel. He discovered that there's also these crazy salts that you could keep in your pocket that would do the same frickin' thing, right? So underneath the umbrella of radiation, stuff that likes to move it, right? We've got two camps. We've got the electromagnetic camp over here that's beating people with a rubber hose, right? And then we've got this weird radioactive salt camp over here that's like contaminating everything. That's why I put this weird looking My Little Pony on here. She's sitting in this bucket of radioactive goo, right? This stuff is weird. So it is particles, it's atoms that are doing energy. They are doing work. They are atoms capable of doing work. And if you want to know what type of work they're doing, it's borderline occult type stuff, right? I don't know if anyone remembers the original Smurfs cartoon, right? But there was a wizard on there named Gargamel.
Yeah.
Now, why did Gargamel want the Smurfs?
He wanted to eat them.
He didn't just want to eat them, right? I think his cat Azrael wanted to eat them. Which, by the way, Azrael is the name of the angel of death, which I think is an awesome name for a cat. But Gargamel wanted the Smurfs because he could use them to turn lead into gold, right? He was an alchemist. So back in the Dark Ages, there were people who sat around and did dark, strange things in order to figure out how to cause the transmutation of metals, right? In fact, Sir Isaac Newton practiced alchemy. So this is not a remote science, right? Interestingly enough, right, there was a Russian scientist who defected to America, and you know who helped him defect in the 1980s? The Church of Satan. I'm not making this up. The reason that Anton LaVey, the high priest of the Church of Satan, wanted this guy to defect is because he understood that if he's a radiation physicist, he understands modern-day alchemy. He called this a modern-day black art, right? So we're on top of some weird stuff here. I want to stress that. On the one side, we had electromagnetic stuff that's clean. You can turn it on, you can turn it off. It works just like a light bulb. And on the other side, we have some weird stuff going on, and that's the particulate side of it. So all of it's under the umbrella of radiation. One side of it's fairly clean, X-rays. The other side of it's pretty freaking weird. So if you're wondering, can we turn stuff into gold? The answer is yes. We now have the capability of turning things into gold, right? That's what the science of particulate radiation has taught us. The problem is that it's not lead that we could turn into gold. It would have to be platinum. We can turn platinum into gold and make it radioactive, right? And when platinum undergoes radioactive decay, it turns into gold, right? It would continue then to be radioactive and undergo further radioactive decay and become lead. The atoms literally change elements when radioactive decay occurs. They also emit a tremendous amount of energy in various forms. So some of those energy forms that particulate radiation produces is alpha particles, beta particles, neutrons, protons, all sorts of weird stuff that can do all sorts of weird work on people's bodies, right? I'm not going to go into all the details on that right now because we'll talk about it in radiation biology. But pay attention when Mr. Wolf is talking about that. And the reason I'm stressing is because I was like in my X-ray program for like a year before I realized, oh wait, the nuclear medicine people are doing totally different stuff that is totally different from what I'm doing, right? So you might as well understand that right now. Two very, very different forms of radiation, electromagnetic radiation and particulate radiation. So, what does particulate radiation do? And what are ways that we can think about particulate radiation? Well, we are messing around with particles inside of the X-ray tube, right? So we are doing something similar to particulate work when we're messing around with the X-ray tube. We're accelerating electrons, we're causing the electrons to do funny things, and when the electrons do those funny things, they produce X-rays. So we are messing with particulate stuff when we're producing X-rays inside of the X-ray tube. So you can't totally throw out the nuke med stuff. You need to pay attention to Tom's lectures about that stuff. It's still important, okay? And it's helpful to know the different valence shells and how many electrons are at the different valence levels around the nucleus of the atom. So the way that I remember this is this mnemonic that is based on the shell symbol. So we have the first shell is called K, then L, M, N, O, etc. And I just remember electrons are kind of low mass negativities, right? Kind of low mass negativities. And if I remember that in this formula 2n squared, I can tell you how many electrons should be in the valence shell. That will be important when we talk later on about characteristic radiation. Negativities. They're negative. The other reason it's important is because of this, right? What is this? A mushroom cloud, right? Specifically, this is the mushroom cloud that was visible over, if I remember right, Bikini Atoll, right, when we made SpongeBob SquarePants. Because everyone knows that SpongeBob SquarePants came from the U.S. Marshall Islands nuclear underwater tests, right? If you're not sure about that, look it up. It's on YouTube. It's true. So at Bikini Reef, we detonated the first hydrogen bomb. It burned so bright, it literally incinerated the Earth's atmosphere and made this amazing lava lamp temporarily, and also made SpongeBob SquarePants. So when we talk about radiation, we talk about X-rays, this is what our patients are thinking, right? This is what they're thinking about, right? So let's pause here for just a minute and talk about this, right? Because this is kind of has a relationship to what Mrs. Rankin said, right? That there's some kind of work going on here that's kind of creepy. Like she said, I'd seen my death, right? But you'll notice in our timeline, this is not until about the middle of that timeline, right? 1948, 49, somewhere in there. I should know, but I've forgotten right now. The end of World War II. And what's interesting about this is that this is the moment, finally, that people started thinking about radiation safety. So you have all sorts of people being injured by X-rays early on. Thomas Edison pretty much kills his best friend, Charles Daly, doing experiments on him. Early X-ray radiographers, their hands were badly scarred and damaged, and they lost fingers due to working around this stuff. And it wasn't until we used nuclear weapons that people thought, oh, maybe we should practice some safety around this stuff, right? So if our patients are thinking about this, let's talk about it real quickly. What is different between this and what we're doing when we turn on the X-ray tube? First off, what type of radiation is this? How is this made? Is it made with X-rays or is it made with particulate stuff? It's made with particulate stuff, right? and I said, which of them is clean, the X-rays or the particulate stuff? Which one's the clean one? The X-rays are the clean one, right? So this is made with particulate stuff, and the particulate stuff is the dirty stuff, right? This is just how dirty it can get, right? The primary form of destruction that is wrought by nuclear weapons and nuclear bombs is incendiary, right? It's a shock wave. So it explodes, the explosion is very forceful, and the force of that explosion causes mechanical radiation, right? Mechanical radiation to destroy infrastructure, right? Or in this case, an entire island. What remains afterward is some radiation contamination, because the initial explosion was caused by particulate radiation. But the radiation level itself is not all that much, right? So if you were going to go back to this place, are there portions of this area that's radioactive? Yes, that's true, right? But for the most part, the contamination has been distributed all throughout the Earth's atmosphere. So I want us to be aware of that, because it is, when we're talking about radiation with our patients, we kind of have this boogeyman in the room, right? And I don't want us to be uninformed about that. In addition to that, we have the long-term human effects that can occur due to radiation exposure. So there's a need for us to think seriously about protection and how to protect ourselves, and why should we protect ourselves. So when we talk about protection, there's two types of effects that radiation can have on us, right, that we have to think about protection from. The first is deterministic effects. And these are effects that are determined by the dose, right? So the more dose you're exposed to, the more pronounced the effect will be. You can think about it like getting a sunburn. Like, I sunburn really easily, right? If I stay outside for 10 minutes, I'll probably be okay. But 15 minutes, I'm really going to be pushing it, right? 20 minutes, I'm definitely going to have a sunburn, right? So the sunburn was determined by the dose, the amount of time I spent around out in the sun. Also, the severity of my sunburn would be determined by the dose. Now, if I stay out there for 2 hours, I will not be able to go to work tomorrow, right? I'll be in that much pain. So the severity was increased significantly due to the increased dose, right? That's what deterministic means. So in a similar way, radiation can cause burns. In fact, the very first way that we monitored radiation exposure was by a skin erythema dose. That means that you would work around the stuff until it started turning your hands red, and then you would say, it's time for me to go home for the day, my hands are red. So your hands were your dosimeter. And when your hands had turned red, you knew it was time to go home. The problem is that different people's hands turn red at different rates. Every single one of us, right, have different levels of radiosensitivity. This is a photograph of a person who was a first responder, I believe, to the Chernobyl nuclear power plant disaster, and they have burns to their hands caused by radiation that cause loss of capillaries, so there's scarring around the fingers, and they've lost a finger due to necrosis because the capillaries were destroyed and the skin became necrotic, so it had to be amputated. Another deterministic effect of radiation is cataracts, and it is a real thing that can really happen. But the strange thing is there's a lot of people who work around it, especially in the cath lab, where they're exposed to doses that can produce a cataract, but they don't wear lead glasses. And I just don't even understand how that's the case. But it's just people's attitudes are different sometimes. Okay, the other form of effect that radiation can have on organic matter is stochastic effects, and this is kind of the weird one, the one that's hard to wrap your mind around. But if the first one was like getting a sunburn, this one's more like going to Las Vegas, right? In Las Vegas, there's these places called casinos. Maybe you've heard of them. And inside of these places, you can put money on a table and they will take it from you, right? Immediately. And people do this a lot. It's very fun for them. In the process of taking your money, though, they spin this thing around and then they take your money away from you. So I think part of it is that people like watching the thing being spun around, right? The thing that they spin around is called a roulette wheel, right? So every time you get an x-ray, you spin the roulette wheel, right? And it's possible that one of the numbers the roulette wheel will land on will be called cancer, right? It's very possible. It could happen the very first time you spin that roulette wheel, or it could never happen ever. You could spin the roulette wheel over and over and over again and not get cancer, right? So I think about like life at the cancer casino, where we're all sitting around spinning the roulette wheel with all sorts of things, not just with x-rays, but every time we pump gas, we're spinning the roulette wheel. Every time we put hairspray on our hair, because I know how much y'all like hairspray, you're spinning the roulette wheel, right? All of these things potentially can contribute to causing cancer, right? But they are stochastic effects, which kind of means they're kind of like random, right? The odds are if you spin the roulette wheel enough, eventually you'll win, but the odds are also in the house's favor, right? There's enough processes in place that will prevent us from getting cancer. The other thing that's a stochastic effect would be genetic mutation, right? So I got this picture of these weird flowers here, right? So our patients are like, well, what does all this add up to, right? Like, that's all great and well, but you're kind of freaking me out. So how do we talk to them about radiation? I do not mention nuclear bombs going off, right? I don't mention that Roentgen was a werewolf and that his wife was a vampire, although I find that very interesting and important. But I do mention largely positive things related to the ways that we work around this stuff. First off, we've got policies in place. Every facility that you work at has radiation protection policies in place, right? We have technology that we've demonstrated should be enhanced over time, right? And it continues to be developed and enhanced. We can make goals for ways to reduce dose for specific procedures. Honestly, we've not been very good about that. And one of the reasons we're not good about it is because we've yet to put safety in the budget, and we're not documenting jack crap, right? So the only thing that we report right now in terms of patient radiation dose is excessive radiation dose, right? If their patient is burned, then we have to report that. So we're kind of still, you may be wondering, oh my goodness, all those people, they were getting burned, they were messing around with x-ray tubes, and their hands were getting burned, and they didn't care because they were so dumb, and people were dumb, they had dumb dresses back then, right? All those kinds of things. Well, guess what? We're still dumb, y'all. Like, we're still doing the same dumb stuff, right? We didn't learn all that much, besides the fact that SpongeBob is kind of funny. The best way to talk to patients about it is that, number one, radiation is part of the Earth's environment, right? It is around us every day of our lives. And the benefits of today's procedure far outweigh the risks, right? You can say that without lying about pretty much anything that we do, unless what you're doing is a PET CT on a baby for some crazy reason, right? Which no one would ever do anyways. So the amount of radiation that we're doing and that we're using, for example, with the chest x-ray is about equal to 10 days of natural background radiation, right? And the benefits of a chest x-ray is that it can let us know, do you have cancer? Is your heart in heart failure? Or do you have pneumonia? Do you have any of a number of chronic or acute conditions, right? We can make over 500 different diagnoses based on a chest x-ray. So that's the discussion of different types and effects of radiation. It's also helpful to understand that there's different sources of ionizing radiation. There's the natural environment, which is things like cosmic rays, terrestrial radiation, internal radionuclides. Every time you eat an avocado or a banana, there's going to be some radioactivity floating around inside of your body. And then there's man-made stuff, right? Man-made stuff would be stuff like the x-ray machine that I just talked about. Industrial uses of radiation, like cesium-137 that they used for every single road outside of this facility. They measured the moisture content of the roadbed using cesium-137. So we live in an atomic world now, and we're using it with all sorts of consumer products. That fire detector above your heads is an alpha particle emitter. You know, all sorts of stuff in this room is radioactive, right? The sheetrock in the room, all that stuff. And then, of course, nuclear power. If you're curious, though, with all these different sources of radiation, where does the fault lie? The most recent report on this came out based on data from 2006. It's NCRP report number 160, and this still guides a lot of our thinking about radiation safety now. So this pie chart, if you're looking at it, this part from here to here is the naturally occurring radiation sources, right? This large chunk right here is radon. The large red chunk is radon. So radon is a significant way that the U.S. public is exposed to radiation from natural sources, right? So we don't have to worry about that so much here in Memphis, but if you lived, for example, in East Tennessee or in Colorado, you would need to have, before you purchase a house, some radon detection done, especially in the basement. Because there are some places where if you're sitting in the basement of your house, you're being exposed to quite a bit of radon, right? It's a gas that comes up from the earth. The other side of the pie chart is all of the medical stuff and industrial stuff and everything except for air travel, pretty much, is on there. If air travel's on there, it would be kind of interesting to look at that. But the biggest piece of the pie now is computed tomography, right? CT. We're ordering a lot of CT scans. So in terms of what you can do for yourself and what you can talk to your patients about, it is ALARA. And ALARA is now a legally defined term, right? We can ask in the court of law, was this individual practicing ALARA, right? And that has now legal precedence. We can say yes, no, maybe, I don't know, right? But ALARA most readily translates for me, how do I practice ALARA? Well, I minimize the time that I'm around radioactive stuff. I increase my distance from it, and if necessary, I will use shielding, right? So that's how that does guide me in practical applications of ALARA. The distance piece is important, and this is why we need to kind of have a review of math, is thinking about the inverse square law, right? But all this is saying is that the intensity of radiation falls off as you increase your distance from it, right? It falls off exponentially. And the reason I can say that is because it has those exponents in there by the d, right? So these type of formulas have been worked out in a number of different ways. I'll work one out for you really quickly. But I like the way it's written out across the bottom. The intensity 1 is the intensity at distance 1, D1, from the source, whatever the radiation source is. Intensity 2 is the intensity at distance 2 from the source, right? So if I say this skeleton was radioactive, right, that I'm standing by, and let's say that I'm standing 2 feet away from this radioactive skeleton, right? Then my dose, let's say at this distance of 2 feet from the skeleton, is 6 milliroentgens per hour, right? 6 milliroentgens per hour. Let's do the math. I'm going to zoom in here and we'll work this out. And you're going to have to excuse me because I write like a 6-year-old when I'm using this thing. Right? So I said for intensity 1 at 2 feet from the skeleton, my exposure rate was what? Did I say 6 milliroentgens per hour? 6 milliroentgens, and I'm not going to write the per hour. And I don't know what intensity 2 is, right? I've not yet assigned that a distance, so I'm going to put an X down here, right? But at distance 1, I said was 2 feet, right?
Yes, it's showing it.
What? Oh, you can't see it. I can see it online. Is 2 feet all I write? What else do I write? squared. 2 feet squared. Please don't forget that squaring. So if I wanted to do a little shortcut, I could just write 4, right? Good. All right. Now let's say that I'm standing 4 feet. I doubled my distance, right? I doubled my distance from the radioactive skeleton. But is it just 4 feet?
Square.
Oh, thank you. Don't forget that. So 4 feet squared, right? And what I'm curious about is what happened to the intensity of the radiation that I'm exposed to. Now, y'all are good scientists, right? So I'll ask you this. What would I expect the intensity of the radiation to do? It would go down. I'm expecting that it's going to go down. Thank you. I would expect that it would decrease. I'll put a little arrow there by it. So I'm reminding myself, in case I, like between now and solving this problem, something else happens, someone runs in there with their pants on fire, I can remember I would expect that my intensity would decrease, right? So this is where it's helpful to have a little bit of math on board, right? Because what we're going to have to do is some cross multiplication. So the next level down, I'm just going to put 6, and I'm going to put that over x, and I'm going to put, what's this, 16 over 4, right? I'm going to leave it at that. So 6 over x, 16 over 4. All right? Now what do I do?
Cross multiply.
Yes, cross multiply. So I can cross multiply to figure out what x is, right? Let me move this little screen up. So now I've got what? 6 times 4, 24, is that right? So 24 equals what?
16.
Good. 24 equals 16x. Now I can figure out what x is. How am I going to do that?
Divide 24 by 16.
Okay, divide 24 by 16. And what do I get? Hmm?
You get your calculator out.
Yeah, someone get a calculator out.
1.5.
Hmm?
1.5.
1.5 is it?
I think.
Yes.
1.5. 1.5. Boom. 1.5 what? Milliroentgens per hour, we said. Milliroentgens per hour. This is my dose rate. It went down, right? To what degree did it go down? A lot. In fact, we can say exactly how much. It went down by a quarter, right? It is now 25% of what it originally was, right? So when I doubled my distance, my dose rate was reduced to 25% of what it originally was, right? So I can think about this in terms of quarters when I'm messing around with it in terms of doubling it. So here's another example. This dog is being irradiated by this robot. And in this situation, in both cases, the dog is probably thinking, hey, right? But which one of these dogs is being irradiated less? He's the smart one, right? I need to show this to my dog at home because he's been barking all night long. This is what's going to happen to you if you keep barking at me. Now, the reason I'm kind of talking about all this stuff, right? So I've said that if you're working around x-rays, if you're working around a radioactive skeleton, try to stand at least, right? It's a lot better to stand 4 feet away from it than 2 feet away from it. Like if I'm standing here, it makes a big difference if I just do that, right? A big difference. We are not necessarily always aimed at reducing the dose at all cost, right? The one thing that we don't want to reduce the dose at the cost of is diagnostic efficacy. So I used to think all the time, I could, as a CT tech, I could lower the dose all day long and get you crappy pictures all day long, right? We need an optimum amount of dose to get pictures that are going to show us what we're trying to look at. So it won't help us out at all if we have a really, really low patient dose, but we missed a diagnosis, right? So the goals that we're going to follow will be optimization of the dose. What is the optimum dose for this exam? Justifying the procedure. Is this the right exam to be doing on this person? Like I jokingly said earlier, something about a PET CT on a baby. Really bad idea. Why? Because it can't be justified. And then limit the exposed population. So if we go back a few slides to that very first x-ray, right, taken at Dartmouth, we've got the boy in the room, we've got his mom in the room, you got this two guys in the room who are just staring at things. Like, yeah, that's a problem. We don't need everyone in the room when we're taking an x-ray. So we also have some limitations here, right? And I just want to point one thing out. So this is NCRP report number 116, which guides dose limitations for us as x-ray techs working in the United States of America, right? The effective annual dose that you're permitted to get once you're a licensed x-ray tech is 50 millisieverts annually. You should not get anything more than that, right? It's not like you're trying to get that amount. You want to get something significantly less than that, but you should not exceed that amount. It's a limit, right? For you right now, as a x-ray tech student, your effective annual dose limit is 1 millisievert. Now, how is that fair, right? That just because I went to school, now I can get 50 times the radiation dose as you guys. Like, what special bus did y'all come to school on, right? What's happening here? Well, it has to do with thinking about things based on population size, right? So basically, there's a whole lot more of general public in the United States of America than there are x-ray techs. So if you look at the population of x-ray techs versus the population of the general public, the x-ray tech population is smaller. And so it's assumed that that smaller portion of the larger population could receive a larger dose. And then that would just kind of wash out over the entire population. These are the dose limits that we currently use, though. You'll notice the ICRP, so that's the International Council on Radiologic Protections and Measurements, which is what guides most of Europe, has effective dose limits that are lower, right? And in fact, there's some countries you can work at where you actually get hazard pay for working as an x-ray tech. So things to consider next time you go to vote. I mean, I'd love to get hazard pay. I think y'all are a hazard, I would say. I mean, that poor security guard, he's probably still scarred by. Okay, before we start thinking about all that though, so with that last slide, I started talking about 50 millisieverts, 20 millisieverts. What the heck is a millisievert? Like, what does that even mean about anything, right? It's not a super helpful thing. It's much easier to talk about a chest x-ray, for example, is like 10 days of natural background radiation. I have an idea what 10 days feels like, right? Like this lecture probably feels like about 10 days long to you, right? That's about 10 days, right? Versus a chest CT, right, is like 1,000 days of natural background radiation. That makes sense. Right? That's a way of making sense of this stuff. We're going to use some special units of measure, right, to understand this stuff. And the way that these special units of measure are built is we start at basic quantities, like stuff like mass, time, and length, then derived quantities like velocity, and then finally special quantities, right? And that's where the world of radiation exposure lives, is up in the area of special quantities. So for example, I said at the very beginning that radiation has the ability to do work, right? So we've defined it based on that. The gray is joules per kilogram, the ability to do work over a kilogram of substance, right? That's how we're defining absorbed dose. I like this Christmas tree. So we'll also use these scientific prefixes that everyone hates, right? So go ahead and just hate on them now. I don't care if you hate them. I love them. I would marry them if I could. I would marry the SI units of measure if I could, right? It doesn't reply to my emails though. And we've got all these weird radiologic units. We've got the customary units. This chart must have been made in Great Britain. And then we have the traditional. So traditional, customary, you could use those interchangeably. Because here in the United States of America, we like measuring things by the king's foot and the king's mile, right?
Not King Cotton.
Not King Cotton, though. Forget about them. So we are still wedded to traditional units of measure, right? We are still wedded to these traditional units of measure, including the Roentgen, the RAD, the RIM, the Curie, things like that, right? Most of the rest of the world drives a certain amount of kilometers per hour, right? And all those people who are driving kilometers per hour on the wrong side of the road are also measuring things in gray, sieverts, and becquerels, right? We just like to be confusing. So you're going to need to be able to convert. That's the long story short, right? Yep, it happened. This is how I remember it, that 1 rad equals 1 centigrade. 1 rad equals 1 centigrade, and who cares about the rest of it? Like, don't worry about the Curie and the becquerel. I'm not going to ask you questions about that. And when it comes time to take the registry, guess what? It will have it in both units. I just don't want you to be confused by that. When you're taking the registry, I want you to have some idea. And it will be in SI units, because the registry wanted to be the weird ones. They're close to Canada, so they took the Canadian option. Now, last thing I'll point out to you is this is led to what we call radiophobia, right? This stuff's confusing. There's units, science. He said something about the king that was offensive to me. All of these things are confusing, right, to the general public. Just like this photograph is a total hoax. This is Photoshop, y'all. This has nothing to do with genetic mutation, right? So a lot of what we say about radiation and radiation mutation is completely false, right? There's a lot of ways it's been popularized. It does not cause zombies. It did not cause Godzilla. It does not make people glow in the dark. All of those things, those popular understandings of it, are false. Equally false is that you should just let the government take care of it, right? Probably also false. I would say educate yourself. Radiation need not be feared, but it must command our respect. And the best way that you can communicate all this confusing stuff to people is to go back to the fact that it exists in the natural environment. It's part of the world that we live in. It's been here since the time of dinosaurs, right? And life has evolved or developed in its presence. And so I can say in all honesty to a patient, the exam that we're doing today, this chest x-ray that we're doing today, is about equal to 10 days of natural background radiation. Or I could say the chest x-ray that we're doing today, this 2-view chest x-ray, would be like a flight to Paris and the return trip in terms of exposure to cosmic rays from being in an airplane, right? And people can understand that. Versus a chest CT would be like 100 flights to Paris. And the free stuff, I know that you're all anticipating, is this book, The Shadow Makers. It's an amazing book. I really enjoyed it. That's a picture of Roentgen in a movie. And it's available at the ASRT. You can just Google ASRT Shadow Makers and get this amazing book and read it and enjoy it.